Alright, so this first piece just kind of summarizes what we ended with in that last video with the different types of multiplicities. So if it's an even multiplicity, it looks like it bounces off of that 0. If it's an odd multiplicity, well, 1's technically odd here, so if it's 1, then you go straight through. If it's an odd number besides 1, then it flattens through. So that's the difference between having a point, so flattening through goes like that, straight through just crosses through. And then the bounce would be bouncing off of that point. So let's kind of put these pieces together. We're going to do one case where we're given the factored form, kind of putting the graph together and all this terminology we've talked about. And then we'll look at given a graph and making the polynomial. So here we have this polynomial. We're going to describe the degree of the polynomial. So let's start with the degree. So as I talked about, what we can do is just add up the exponents on the outside here. So it's like a 2 plus 1 plus 1, which would be 4. And then I'm just going to make note that this number up front is positive, so we're not having any sort of reflection like I talked about in that first video. So with that, in terms of long run behavior, this long run behavior is going to match x to the 4th, or even x squared, if we think of just an even degree. And what I like to do for that is, once I recognize, okay, this is an even degree, in terms of long run behavior, we should be going off to positive infinity on both sides. So what I do is I just make, usually with pencil, I know I'm on a tablet so it has to be pen, but I just make a note of basically where I know where my graph should begin and end. If it was an odd degree, I would make a note to myself like this, so that I know when I started connecting points, whatever happens in the middle there, it would have to go off like that. But here we have even, so it should both be going off to positive infinity. So I know I'm starting over here, I'm going to do stuff there, and then go off to positive infinity there. And then this usually kind of helps me write the long run behavior. So long run behavior, if we have to write this out, we want to talk about, and the general structure goes as x approaches positive infinity, f of x approaches, and as x approaches negative infinity, f of x approaches. So without evaluating anything, if you're asked for the long run behavior, this is the starting structure of it. And the idea is, as x is approaching infinity, our function is going to go off to positive infinity. So I'd fill in the blank with positive infinity. As x goes off to negative infinity, our function is going to go off to positive infinity. So that's our long run behavior. Maximum number of turning points. That would be taking the degree minus 1, so degree of 4 minus 1, so maximum number of turning points should be 3. We end up with more of those, that shouldn't happen. Horizontal and vertical intercept. So horizontal intercept is the same thing as saying x-intercept. In fact, sorry, let's just do the vertical intercept real quick, which is the y-intercept. Because for that, we're just plugging in 0. So we're looking at f of 0, which is the same thing as taking 1/4 times 0 plus 1 squared times 0 plus 2 times 0 minus 5. So with that, we have 1/4 times 1 squared, which is just 1, times 2 times negative 5. So a negative 10 over 4, which is negative 5/2, or negative 2.5, depending on how you want to write that. So with that, we get the coordinate 0, negative 2.5. Okay. So now I can focus on horizontal intercepts, which is going to be the same thing as zeros, and then we could talk about their multiplicity as well. So x-intercepts, or we could call these the zeros of the function. And what we're really doing is we're solving 0 equals 1/4, x plus 1 squared, x plus 2, x minus 5. And what we get from that is solving x plus 1 equals 0, which would give us x equals -1, x plus 2 equals 0, which would give us x equals -2, x minus 5 equals 0, which would give us x equals 5. But if you want to, you can do that. You can solve each of those pieces separately, get there, or if you're comfortable with it, it's just a matter of going through these and switching the signs. So we're going to have x equals -1, we're going to have x equals -2, and we're going to have x equals and positive 5. Now, in terms of the multiplicity, because x plus 1 is squared, that's going to have a multiplicity of 2. And then with the others, they have exponents of 1, so those are going to have a multiplicity of 1. So what that tells me is that when I'm at x equals -1, there's going to be a bounce. And then for these where it's a multiplicity of 1, we're just crossing through. Alright, so what we have are some points now. We have x equals -1, x equals -2, x equals positive 5. And we have a 0 at -2.5. And in fact, just to make sure I don't go, okay, I'm going to show you as we put this together, but I'll also show you what if I ignore the multiplicity and how we'd get stuck. So let's say I ignored that multiplicity of 2, meaning I'm going to try and go through each of these points right here. So I know I have to start up here, so I just start in this upper left-hand side, and it doesn't have to be all the way over here. I could even scoot it in over here. So let's say I try to cross, but then if my next cross is all the way over here, there's a few things happening then. I'm missing my y-intercept, I'm not even going through that point, and I can't go down and grab that because then I would be creating a whole other 0 that we don't have. Then I could see it. I also get stuck down here and I can't go off to positive infinity there. So if I start making this and I'm like, man, missing points and it's not going off to the long run behavior like it should, that's where we should check our multiplicity. So we're going to hit that 0 of -2 first, so I absolutely do need to go through that point. But then, to go through x equals -1, that's where we have the bounce. So what I'm going to have is, we'll have to turn around to go to that 0, and then we're going to bounce off of it. So we're going to stay on that same side of the x-axis, and now I'm on the correct side that I can now go through that point there. Now I'm going to need to turn and go through that. Oh, I missed it a little bit. Go through that point, and then go off to positive infinity. It's not the prettiest graph, and these were definitely just sketches. What we want to get at are the zeros and that long run behavior. So this is definitely, if we look at the graph on Desmos, it would look very different, or it should look roughly the same. We're just trying to get the general shape going. So that would put all the pieces together. We are crossing the 0, bouncing, crossing, and then the y-intercept is just this extra point that we have that we know we need to go through there. But what I would want to make sure is that I'm matching the long run behavior, and also I should make sure that when I made the graph I didn't suddenly create more zeros, but it should all line up. In terms of turning points, we have 1, 2, 3 turning points, so that lined up great. So that puts all those pieces together. Alright, now let's look at an example where they're giving us the graph and talking about those same pieces, and we're going to find the formula. Or we can even start with finding the formula. Let's go ahead with that. So, finding our formula. I'm going to have f of x equals. Now what I don't know is this possible number out front. There could be this number out front that stretches things out or makes things negative. You want to be careful of that. So I'm going to call that a. I'm just going to leave that as there's this possible number a, and then from there I'm just going to focus on the zeros of the graph. So I have 1, 2, 3 zeros, which tells me I'm going to have 1, 2, 3 factors. Now we have a 0 at -3, so that would show up as x plus 3. We have a 0 at 0, which would just be x. It's like x plus 0 or x minus 0, but we're just going to show that as x. And then we have a 0 at +3, which will show up as x minus 3. Now in terms of multiplicity, at the -3, or what lines up with the x plus 3, sorry about that, since there's a bounce there, we'll have an exponent of 2. We need an even exponent there. Same thing for at x equals 0, it bounces, so we're going to need an exponent of 2. For x minus 3, which is occurring at the +3, we just cross through, so having an exponent of 1 there is awesome. So, we'll fill in the blank for a in a moment, but let's talk about the degree of the polynomial. Now for the degree, we're going to take 2 plus 2 plus 1. 2 plus 2 plus 1, which is 5, which sounds great because even though it's flipped around, we have one side going off to positive infinity, the other side going off to negative infinity, which lines up with the long-run behavior of odd functions. So, long-run behavior, so as x, that last time too, as x approaches positive infinity, f of x approaches, and as x approaches negative infinity, f of x approaches. Alright, so as x approaches positive infinity, so as we're going off to this right-hand side here, our function is going off to negative infinity. As x approaches negative infinity, so as we go off to this left-hand side, our function goes off to positive infinity. There's our long-run behavior. Alright, maximum number of turning points. We take our degree minus 1, that's 4. Vertical intercept, so our y-intercept, the same thing as that vertical intercept, is going to be at 0, 0. You can see that on our graph right there. Horizontal intercepts, the zeros and multiplicities, we basically already said those. So we have our zeros that we marked there, and then we talked about the multiplicity 2, 2, and 1 on those zeros. So, sorry, I just know this video is getting kind of long, and I want to jump ahead to us finishing the formula by finding a. Now something I want us to notice here before we even find a is typically these odd degree functions go like this. They typically start at negative infinity and then go off to positive infinity. That's the general shape. As we can see, ours is doing the opposite. If I ignore the short run behavior, ours is going the other way of positive infinity to negative infinity. So what that tells me is that when I find a, it should be negative. that's going to give us that flip that I showed us in that first video. So with that, I kind of have an idea of what A should come out to be without actually finding it yet. So to find A, that's why they've marked this point right here. There's this coordinate right here at 1, 2 that's going to help us out. And what we're going to do is where we basically have our entire polynomial function there in our factored form, we just have this missing piece, but what we can do is plug in the x value, plug in y from that coordinate. So we're going to do, plugging in that coordinate, we'll have 2 equals that unknown a, and then 1 plus 3 squared times 1 squared times 1 minus 3 squared. And then we're just going to solve for a. So 2 equals a times 4 squared, so 16, times 1 squared is just 1, 1 minus 3 squared, so negative 2, squared is 4. So 2 equals a times, and 16 times 4, 32, 64. Divide both sides by 64. And reduce that fraction. And where did my negative go? Aha! See, that's why it's so good I made that note to myself that it should be negative. And you may have been screaming this all along as I was doing this wrong. There shouldn't be an exponent of 2 there. So I need to go back. But I saw I was going to get a positive number out, which I knew shouldn't happen. So that's where it's good to have some instinct with this. Okay. So I messed up by putting an exponent of 2 there where we said the multiplicity should be 1. So let's try this again. 2 equals a times 1 plus 3 squared, 4 squared 16, times 1 squared, times negative 2. Alright, 2 equals a times, and that's a negative 32. Divide by negative 32, divide by negative 32, and there's our negative. So a should be a negative 1 over 16. So, from there, what we'll have is our function. We'll have this value out front of negative 1 over 16. And then typically, and this isn't a big thing, but this x squared typically goes out front. So I'm just going to throw that x squared right there, so it'll match the notation that you'll see. And then we'll have x plus 3 squared and x minus 3 not squared. And that would be our function there. So what we could do is when you get to the end of this and you're like, gee, I hope I did that right, plug it into the graphing calculator and see that those points come up, that the behavior's working the same, and that it just all balances out.